All right. Okay. Before we go to the mechanics of material, there is one thing which is kind of well, two things actually. So let's do one simple problem where I have say for example you have a roller support here and there is a hinge support, and this thing is being loaded by distributed load. It's a triangle, it goes all the way to 0 here like this, and then we have 150 pound per feet, and we are given with this distances not to the scale. This is 6 feet and this one is 8 feet. So this is another type of problem that you will see, which is kind of not that much covered in your review manual. So for example, if you have a load distribution like this, there are few types of problem that you can have based upon this distributed load. The first thing would be, what would be the resultant force acting on the beam and where is that? So first of all, we all know it's a distributed load, meaning the load itself is changing from point A to point B. In this case, let's give them some name, A to B. And the second thing is, since it is changing from one point to another point, how would we define what would be the resultant force and where it would act? So to do that, what we need to do is, what we have to do, if I want to get the net resultant force acting on the beam and where it is acting, centroid, right? So essentially what we are doing is we are making use of the centroid. So we are saying this is a triangular distribution, right? And the other one is rectangular. So what we can do for the green portion, we can come up with the force, resultant force of the green portion, which is 150 times 8. What would be that number? 150 times 8 would be 800 plus 400, 1200, right? So we have 1200 pound acting where? Right in the middle, because it is uniform. And for the triangle, what would happen? So you will have a force which will be, again, that force would be the area of the load diagram. In this case, 6 times 150 times 1/2, and how much we get? 450, right? So essentially what we are doing now, this distributed load is being replaced by point loads. So we have 2 point load, 450 and 1200. So where would be the resultant force of these two acting? Somewhere in between, right? And how much would be that force? That force would be exactly equal to sum of these, which is 1650, right? So 1650 pound force will act where? Somewhere. And in fact, that 1650 is going to act at the centroid of the load distributed load diagram that we have. So in fact, this thing that we are trying to find out is nothing but is the centroid. So new force is going to act at the centroid of these individual force. Now we can see the use of the centroid concept here. Well, how would we get the XC if we wanted to? You will simply take the moment about, for example, point A. And what we are saying, as we discussed, the definition of the centroid is the moment of the resultant, meaning in this case 1650 times XC, right? That's the moment of the resultant force, must be equal to moment of the individual force, 450 times 2/3 of a 6, right? And 1200 times that distance is going to be 10. Right, and all of them are negative, right, about point A. So if you want, you can put everywhere negative, 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 and that will give you the XC. And how much we get for XC? I have 8 point something. 0.36. Right, so this is basically making use of the centroid. We know the location of the centroid. That's how we find out by comparing the moments about any point you want, right? The moment of the resultant must be equal to moment of the individual. So in fact, that's how the centroid is defined. All right, so another case which is also useful, say if you wanted to find out, even in the same problem we will use, if I wanted to find out the reactions at supports A and B. So what would happen at support A? What type of reaction is going to happen? Just one reaction, right? Maybe let's call that as AY. Since it is the roller support, all you will have is AY. And at point B, what you will have? Some in the X, some in the Y. BX and BY. And now if I want to find those reactions, all you have to do is the equilibrium of the entire structure, right? Entire structure meaning we immediately know AY plus BY must be equal to what? 1650. And also there is nothing in the X, so BX has to be 0. And now how would I get the AYs or BYs, any of them? By taking moment. So we can take the moment about any of the points because we know the moment about A is going to be 0 or B is going to be 0. If I take the moment about B, you can take A for sure. So what we are saying, sum of the moments about point B must be equal to 0. So what does that mean? AY times 14, right? And is that a positive or negative about point B? AY times 14 about point B, negative or positive? Negative? Negative? Come on, somebody else say, is that negative? Yeah, it is negative. And then you will do the other one, 450 times, again assuming that you did not know the information, now you know that, so you could directly use XC, but if you do not know, you will use 450 times 6 plus 2, 8 plus 2, right? 10? Is that right? Since this distance is going to be 2, 6 plus 2A, and then this is going to be positive or negative? Positive, and then you have positive 1200 times that distance is 4 must be equal to 0, and that will give you AY. AY is 1200, is that right? How much? Make sure to divide with, what did I? Yeah, 14. No, not 1200, something else. Sorry, that's a different number. How much we get? 664. I was looking at the wrong. 664 point something? 0.3 pound. And obviously, once you know AY, you could get the BY from there. Since we have it, let's complete it. It would be how much? 1000. What? 7 or 5 point something? No. 5.7? 1005, right? No, maybe not. No, not that. How much? 985.7. So now we know, again, when you have a distributed load, again, your book does not have that many problem on that, but these are really important problem that you can see with the distributed load, which uses the concept of the centroid and also a little bit of what we discussed earlier, forces and the moments. I think, is there anything else that I have? And one more problem that I would like to do with respect to the frictions. And say again, for this I'm going to draw just a simple example the way the problem looks. So you have a 90 kilogram box P, and the problem says this: mu s equals 0.5, mu k equals 0.4, and the question is, if P equals 400 Newton, what is friction force? So basically we are solving for friction force, and again you can have variety of these problems, and again just understanding the basics of the friction will help you solve this problem. So we have a 90 kilogram mass of the body. So what we have to do if P equals 400 Newton? What is the friction force? First of all, what would be the friction force? It will depend upon the normal force, right, as we know, and the normal force is going to be equal to mg, which is 90 times 9.81, right? Oh, come on. How much we get? 90 times 9.81? 883 point something? 883 Newton, right? And if that is the normal force, now this is also going to be equal to normal for us. So what would be the friction? So we immediately know the friction force is static. There is two types of friction that we can have. Friction force is static, can be less than or equal to 0.5 times 883. And what is that number? How much we get? 441.5 pound. And let's also understand the F friction kinetic is going to be 0.4 times 883, right? And how much we get if I do 0.4? 353.2. Oh, these are all Newton, not pound, right? Now, what is the answer? So if P equals 400, what is the friction force we have in this case? $400, right? And if problem says if the P equals 500, then what is the friction force? This is a little tricky problem now. What would happen if I apply P equals 500 Newton there? Remember, when you go 500, you exceeded that limit, this will start moving. And once it starts moving, then you are going to get the kinetic friction, because now your friction is on the moving thing. It's not a static anymore.